So we shall finish the remaining filters today. What will happen for this one? I think last time we just started it. For this, what would be the, if obviously it is very now made amply clear that the input is sinusoidal. So in that case, what we find is that output j omega L upon R plus j omega L. Output is j omega L upon R plus j omega L into V in T, which is sin omega T. VOT is equal. It results into, by rationalizing we get that is equal to j omega L into bracket R plus, is it right? J omega L upon R plus j omega L. J omega L into bracket R minus j omega L upon R square plus omega square L square. Is it right? Into sin omega T. So this is what? One upon R square plus omega square is common into bracket this j minus 1 omega square L, that is it works out to be what it is, or we can have omega L is common. Omega L is common, right? Omega L is common into bracket. This becomes then multiplying what it is, what it comes out to be, JR, right? Omega L will be made common into JR into plus 1. Is it right? Is it okay? JR into plus 1, which we can write as 1 plus JR. Into sin omega. Is it right or some mistake is there? J omega L upon R plus J omega L multiplying by this way, or anyway somewhere some mistake might have been there. To make it very comparable with previous one, there is nothing wrong, but here we make a small change. VOT is equal to j omega L upon this. We divide by this one. J omega L, we take it below. Just means it's just some kind of jugular, nothing else. VOT is equal to 1 upon R upon j omega L plus 1, right, into sin omega T. That is equal to now 1 upon 1 minus j into bracket R upon omega L. Agreed? R upon j omega L multiplying j, so that minus 1, I hope, is it right? Into sin omega T. And then we rationalize. When we further rationalize, it is 1 plus j into bracket R upon omega L, and in the denominator what it works out to be? 1 plus R square upon omega square L square sin omega. So then it is 1 upon 1 plus R square upon omega square L square as it is into bracket, what is the magnitude? It is A plus JB into sin omega t. It is under root A square plus B square sin of omega t plus tan inverse of b by a. So it is 1 plus r square omega square L square under root, right, into sine of omega t plus tan inverse of this upon this, tan inverse of r upon omega L. Is it right? So when that we cancel this root and this one, so it is 1 upon, it is same as previous, 1 plus r square upon omega square L square sine of omega t plus tan inverse of r upon omega L. What is a omega? A omega is this and phi omega is this. So how we plot a omega and phi omega? What is a omega? A omega is one upon under 1 plus 1 upon root 1 plus r square plus omega, r square upon omega square L square. So a omega is 1 upon under root 1 plus r square upon omega square L square. It's very simple. What will happen at omega equal to 0? What will happen at omega equal to 0? At omega equal to 0, denominator will become infinite, right? So a omega will become 0, and at omega equal to infinity, denominator will become 1, right? At omega equal to infinity, this term will become 0, so this will be 1. So it is exactly replica of previous one. For low pass filter, at 0 gain was 1 and it was asymptotically going down to 0 when the omega was approaching infinity. It is exactly reverse, like this. And at like this. And at omega L equal to R, at omega L equal to R, that is at omega equal to R by L, at omega equal to, it would be 1 upon, some mistake is there in R, in omega square, just verify previous one. Yeah. Oh. J omega L upon R plus J omega L multiplying by this 1 upon R by J omega L plus 1 minus. Okay, anyway, right now if some calculation mistake is there, let it remain. 1 upon and what happens to phi omega? Phi omega is tan inverse of R upon omega L. So at omega equal to 0, what will happen? At omega equal to 0, R upon omega will be infinite. So tan inverse of infinity is pi by 90 degrees. So it will be 90, and then R upon omega will be 0. So tan of 0 is 0. So this is the phase response. At like somewhere we made, I'm right now not recollecting, but what was the frequency for RC filter? At what frequency it has become 1? Okay. So when R by L is, if R at omega equal to R by L, this becomes 1. So this becomes 1. So 1 upon 1 plus 1 square root. So 1 upon root 2. So this is the cutoff frequency. And this is now called as lower cutoff frequency. Why? Because it is high pass filter. It is high pass filter, means at lower frequencies it offers less gain, at higher frequencies it offers higher gain. It is high pass filter. Then we move around to next one, which is quite interesting. And here you put an amplifier gain 1 and then you put so what would be VOT? Can you compute? What will happen? Right now we don't go into exact details because it will again take unnecessary time. It is not that unnecessary, it is quite necessary, but looking at the present context, you may not be in a position to afford the time. So what will happen? Suppose that this RC combination is such that its characteristic is like this, and this RC combination it is reverse way. So this is a low pass filter, this is a high pass filter. This is low pass filter, this is a high pass filter. A low pass filter like this, and this is having a characteristic of like this. And these are cascaded. What will happen? What will happen? Means if you derive the complete expression, you will find that filter is a frequency selective network. The output is sine wave only. A omega, if sine omega t is the input, A omega sine of omega t plus phi omega is the output. A omega is some function of omega. For low pass filter, it is high at lower frequencies, low at high frequencies. At low pass filter, it is reverse. If we cascade these two, then A omega will be of a peculiar type. What by common sense you should be able to answer. What is that? The product would be at low frequency it is low, it increases and again reduces. It is a band pass filter. Means below certain frequency, gain is low. Between some band, gain is moderate. And above certain frequency, gain is again low. It's a band pass filter. And if now I have got a low, if I get a next circuit which is having a characteristic like this, I got input that I connect to one low pass filter, the same I connect to one high pass filter, and if I add these two, what will be, if the low pass filter is of this kind, this, the high pass filter, this is the upper cutoff of this low pass filter is having very less upper cutoff. And this high pass filter is having very high lower cutoff. So if I add these two, then in this frequency range this would be available, in higher frequency this would be available, so their net effect would be like this. So it is called as band stop filter or band reject filter. Band stop filter, band reject filter. So low pass, high pass, band stop or band reject. So this is the filter, so which is a frequency selective network. So now I think by looking at the enthusiasm, in fact you should be congratulated.